Now the output from the fast amplifier is fed back through feedback resistor R1873, holding the base of Q1874 constant, so that both amplifiers are under control of the feedback circuit, providing a uniform linearity for the two parallel amplifiers. Well, let's see if we can get the polarities straight. We said that in order to unblank, we would increase the current, and let's go back to the input there at Q1805. Let's take electron flow. We're increasing the current through that transistor, which in turn increases the current through Q1808. Its collector in turn would pull up, which turns on Q1824 harder. Its collector pulls down, which turns on emitter follower Q1827 harder. Now let's take the fast path. That then would pull down on the bases of the parallel transistors. Turning them on harder, the collectors would pull up, which couples through C1850, pulling up on the emitter of Q1854, which pulls up on the collector, and that's the positive going unblanking waveform. Now the slower path would cause Q1874 and Q1876 to draw less current. Now as the unblanking waveform terminates, then Q1874 and Q1876 would turn on and pull the output from the amplifier down. Now during that time, the fast amplifier would be conducting less current. We get a negative step coupled through C1850, which would drop the emitter of Q1854, which would tend to turn that transistor off. Under that condition, then current is supplied through the shunt resistors R1851 and R1852. There are some protective circuits in case the CRT grid is shorted to ground. Now let's begin right at the CRT grid. There at pin 3 to the left is C1884. All right, the right side of that capacitor would be at about minus 3 kV, the left side at something above ground. So the cap has about a 3 kV charge on it, and if you shorted the grid of the CRT to ground, then you'd have a positive 3000 volt step coupled right to left through that capacitor. As soon as that point begins to rise, CR1858 turns on at 70 volts or so and dumps the charge into capacitors C1857 and C1856. Now if it should reach over to the base of Q1854, then CR1855 would come on, protecting the base emitter junction of that transistor. Now let's go back to the output from this circuit, and that positive step, or what's left of it anyway, would pass off to the left through feedback capacitor C1873, through C1871, and is then caught by CR1828. And the balance of the pulse then would pass to ground. Before we leave this circuit, notice that all of the tweaks, there's C1871, which touches up the compensation of the feedback amplifier, then the emitter bypass circuits, C1842, R1842, and then the earlier instruments, R1844 and C1846, are all used to shape the leading edge of the unblanking waveform at the various sweep speeds. Let's look at the CRT grid supply. Now it's stacked on top of the cathode supply. That is, it will be more negative than the 3 kV cathode supply. It uses the DC restorer circuit, and in effect gives one DC coupled unblanking and Z-axis. Well, let's begin way off to the upper left-hand corner where a secondary of T1310 supplies the cathode supply voltage doubler. We'll get back to that later. Also supplies the post-accelerating anode multiplier. We'll get back to that later. But a line goes off to the right there in through R1618, R1619, and so on, and that's what we're interested in. Now it's a sample of the converter voltage with a peak-to-peak amplitude of about 3 kV. Okay, it passes to the right through those two 1.3 meg resistors, clear off to the right, down through R1671, R1672, and will be limited in its positive excursion by CR1676 and in its negative excursion by CR1680. The positive excursion is set by the CRT bias control at, about 100 volts or so. Design center on that control is 90. The negative excursion at whatever the output from the Z-axis circuit is. Now, with the intensity control fully counterclockwise, they'll set at 6 or 7 volts, and with full unblanking at about 60 volts. The limited waveform at the junction of those two diodes will be a square wave. Now let's sketch a few cycles of that square wave. Start in with 2 or 3 cycles whose positive excursion is 100 volts and whose negative excursion is, let's make it 10. Now after 2 or 3 cycles, let's assume that unblanking occurs and the negative excursion pulls up to, say, 50 volts. In other words, the positive excursion will remain at 100 volts. The negative excursion of the square wave will now be at 50 volts. Run 2 or 3 cycles at that amplitude, then drop down to a negative excursion of 10 volts. Now that's the nature of the waveform during one unblanking pulse at the junction of CR1676 and CR1680. Now the net result is the grid waveform, which will be added to the cathode waveform, such that in this case, prior to unblanking, the CR3 grid will be 90 volts more negative than the cathode. During unblanking will be 50 volts more negative than the cathode. In other words, we've unblanked the CRT. Now since the cutoff bias will vary with different CRTs, then we need the CRT grid bias control to compensate. All right, let's begin with the first positive excursion, which pulls up on the left of C1678. Now the right side of that capacitor is clamped by CR1682 to the cathode level. So CR1678 takes on a charge. Plus on the left, minus on the right. 90 volts in amplitude in addition to the 3 kV that was on there originally. Now as the negative excursion arrives, it drops the left side of C1678. The right side also drops, turning off CR1682, turns on CR1679, and dumps the charge into C1680. The charge on that capacitor, in addition to the 3 kV that was there originally, will be equal to the peak-to-peak amplitude of the square wave applied. Now that's 90 volts then, isn't it? Now just as soon as unblanking occurs and the peak-to-peak amplitude of the signal drops to, say, 50 volts, then the charge on C1680 becomes 50 volts. That would be negative on the right. So the Z-axis waveform then appears on the right side of C1680. that voltage drop would be applied across R1684. That voltage therefore appears as the bias on the CRT grid. It has the effect of DC-coupled unblanking and Z-axis. Now fast information takes off from the output from the Z-axis amplifier, couples to the right through C1884 directly to the grid. It's the slower information that goes the route of the DC restorer. Well, let's look at the CRT cathode supply and regulator. Back up to the left to that transformer, T1310. Now that signal that we used a moment ago to drive this limiter now drives a voltage doubler composed of C1607, CR1607, CR1608, C1608. Now the negative voltage appears at the anode of CR1608, a minus 3 kV or so. Now the reference appears to the cathode of CR1607. I'll get back to that in a moment. Notice the filtering through R1609, C1609, R1612, and C1612. And the minus 3 kV feeds off to the right and down to the CRT cathode. Now the reference side of this supply appears at the common collectors of Q1627 and Q1631, the regulator output circuit. Now that can swing with regulation all the way from minus 50 volts or nearly so up to about 128 volts. Nominally it'll set at about 40 volts. Now that CRT cathode supply is a floating supply which sits on top the output from this regulator circuit. So if in regulation you move the reference voltage, then certainly you move the cathode supply voltage as well. Now from the cathode supply off to the right there we have the error divider and cathode bleeder composed of R1640B and R1640A. Those are two parts of a thick film resistor. The error voltage, therefore, drives into IC comparator U1635. The minus side, you'll notice, is referenced to ground. Now, any error voltage, as a result of differences in cathode current and so on, appears at pin 3 of the IC. It's amplified and appears in phase at pin 6, which in turn drives into the base of Q1631, and for fast changes, AC coupled through C1634 up to the base of Q1627. Well, let's see if we can make it work. Let's assume an increased cathode current requirement. The cathode voltage then tends to go less negative or toward ground. Off the error divider in at pin 3 of U1635, that goes in a positive direction. Pin 6 goes in a positive direction, which turns on Q1631 harder. Its collector comes down. Okay, the plus side or reference side of the cathode supply then goes more negative. And of course the minus side of the supply also goes more negative, bringing the cathode back to where it was in the first place. Or since this is an operational amplifier, we realize that this feedback action maintains the cathode potential constant. Let's go back to pin 6 of the IC. Notice that we offset by 51 volts through VR 1635. That drops the base of Q1631 down to where it belongs, one junction above the emitter. Notice the emitter is only 15 ohms from a minus 50 volts. So that sets the level at the base pretty close. Now the collector supply for Q1631 is the constant current supply through Q1627. You see the base of that transistor from a DC standpoint is fixed, and the constant current flowing through the emitter. There's an additional path, however, through R1625. Now, any fast changes in the cathode load is deliberately slowed down by the negative feedback network R1629, C1629. Fast information couples through C1634 to the base of Q1627. Now we have to guard against shorting the cathode supply to ground. Now trouble would occur, well, in a couple of places. Let's look over there by the voltage doubler filter, where that positive step then would couple through C1612 and drive the collectors of Q1627 and Q1631 high enough to damage them were it not for catching diode CR1625. Over at the input to the regulator, we have two more protective diodes, CR1638 and CR1639, to protect the IC at plus or minus 15 volts. And then the output from the IC is limited in a positive direction by CR1635, and on the other side of the zener in a negative direction by CR1632 at a minus 50 volts. Now that seems like an awful lot of protection, but in these high voltage circuits, the protection is necessary because when something shorts, it's hard to predict what will happen without adequate protection all the way along the circuit. Notice compensating capacitor, C1642, right around part of the error divider. Now, whenever fast changes in the cathode supply occur, and we get a fast reaction at the output from this regulator circuit, that information then couples through C1612 to provide the rapid correction. The entire floating cathode supply then moves to make the same correction. Now that time is controlled to the left there by C1606. Now that same 3 kV output from the transformer T1310 drives into times 7 multiplier, as it's called here. Actually, it has 14 diodes in that package, including the capacitors, and an output resistor in series with a 21 kV line over to the post-accelerating anode to current limit that in case that line gets shorted to ground. Notice the beam current sense, which goes over to schematic 9. That's the converter circuit. Then there's another current sense in series with the reference side of the cathode supply, right between R1605 and C1605. Well, let's look at the dynamic focus circuitry. With the dynamic focus circuit, we'll change the focus potential every time we change intensity. Now, since this instrument features display switching, then in any one sweep we could have both A intensity, B intensity, and readout intensity. A selection is made by U1745 on command from the display B command and the vertical and horizontal off command. Now we're going to use the A intensity, B intensity, and readout intensity, and I think perhaps the best way to locate that is over on schematic 2. You find them up in the upper left-hand corner. Those controls also appear on the logic diagram. See, first there's the readout intensity, the A intensity, and B intensity, just 5K pots tied between ground and a minus 15 volts. The line then passes off to the right there. It goes in through schematic 1 and then appears here on schematic 11. Now the IC, U1745, is a readout data switch IC, and on command by logic levels at pins 1 and 2 will pass the output from one or the other of those intensity controls to pin 7 at the output. Now if pin 2 is high, that's vertical and horizontal off command, then pins 11 and 12 pass through to pin 7. That's the readout intensity. Now when that is low and pin 1 is low, Then the A intensity information from pin 9 goes to pin 7. When pin 1 is high, that's the display B command, then we connect the B intensity control at pin 10. Now the dynamic focus amplifier is another non-inverting op-amp. Let's follow the signal path through Q1755, where we have inversion. We then pass through Q1769, where we have inversion once again. 2 inversions means no inversion, I guess. Okay. RF, therefore, is R1760. We then pass through emitter follower, Q1757, to the minus input there at the emitter of Q1755. RA is R1756. The gain of the amplifier, once again, 1 plus RF over RA. Notice the output level adjust is going to move the emitter of Q1757 and therefore Q1755 and change the output level. Now off the base of Q1755 is the focus amplifier gain. Now if we think of that as a voltage drive, we can say that we attenuate the signal as it comes out of the IC and as it is applied to the base of Q1755. If we think of that as a current drive, then some of the current is siphoned off through that focus amplifier gain adjustment. Now let's go back to the output from this amplifier. Q1759 is the slow path through the amplifier. The fast path is through C1762 to the base of Q1765. Now, as in the Z-axis amplifier down below, the output from this fast amplifier also feeds back through the feedback resistor into the input to the operational amplifier, so that it maintains a linearity throughout. Now, speaking of linearity, we don't want a linear response out of this amplifier. Ideally, we want a square law effect. Well, we accomplish that with CR1753 off to the left there, right at the input. Now, some of the current is siphoned off through that diode and through R1753 and R1754. Now, if we pull more and more current, for example, through that diode, the voltage drop across it will change in a nonlinear manner as a result of the square law effect of the diode, resulting in a square law response as applied to the focus anode. Now, as you draw less and less current through CR1753, then CR1754 catches that and helps in that shaping process. Well, we have protective diodes as usual. CR1771 provides base emitter protection for Q1769 in case Q1755 is pulled out of the socket while the instrument is hot. CR1764 provides base emitter breakdown protection for Q1765. CR1768 protects both Q1765 and Q1769 if the focus anode is shorted to ground. Now, coupling capacitor C1778 has about a 2 kV charge on it. Focus anode sets at about a minus 2 kV. So if you short the focus anode to ground, you get a sizable positive step coupled to the left through C1778, which then gets dissipated through CR1768 to ground. R1778 limits the current a bit so that you don't blow that diode. With various settings of the intensity controls, the output from this circuit at test point 1778 there will swing from about 10 volts to 120. Just up above, you'll recognize a DC restorer circuit just like the one we discussed with the CRT grid supply. Again, we use the 3 kV or so output from T1310. Comes down through R1651, R1652, limited in its positive excursion at 130 volts by CR1653, and in its negative excursion by CR1656 to whatever level we have set at the output from this dynamic focus circuit. The focus supply is referenced back to a divider tied between the cathode potential of minus 3 kV and up through that sizable divider string to 130 volts. Notice that in that string is the front panel focus adjustment. The Zener VR1701 and diode CR1701 limits the range of that focus control so that you can't drop the bottom of it below about 200 volts. Now the tap off that divider is the focus preset adjustment, and that is the reference for the focus supply. Incidentally, if you have an early schematic with a couple of neons tied right across that supply, DS 1663 and 64, those have been removed. Now speaking of neons, we have 4 neons in between the grid supply and the cathode supply. They're in series. There's DS 1687, 1688, and down below 1718 and 1719. Now those come on to protect the grid cathode of the CRT from arc over in case those supplies don't come up at the same time or collapse at the same time. The CRT heater is elevated to minus 3 kV so that it doesn't arc over to the cathode, and the resistor is just all that obvious. The first of those neons that I mentioned, DS 1687 and 88, well, just to the right of that is our 1690, that 100K resistor, which ties to the cathode supply, and at the other end to 6.3 volts, well, that's the heater supply. Now, it comes actually from a tap over on the transformer T1310 off to the left. All we have left are the CRT controls. Up at the top is the trace rotation control. The next one at pin 7 is the geometer control. Now that's also tied to the mesh. Then pin 6, which has a minus 50 volts on it, isn't tied to anything in the standard CRT. However, in the reduced deflection CRT, the mesh is split and a portion of it tied to pin 6. The purpose is to reduce a background glow as a result of secondary emission. Next control down is y-axis alignment. There, because trace rotation doesn't affect both the x and y axis equally, and this adjustment compensates for the difference. The next one is the shield volts adjustment, then the astigmatism, and pin 9 is the first anode.
This is the end of side B.